Okay. Now, consider FIR filters. Suppose you have got H z as B 0, then B 1 Z inverse, B 2 Z inverse 2 dot 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 B q Z inverse q, and this is equal to y z by x z. Very simply, y z is x z times the entire thing. So, x z into B 0 plus x z Z inverse into B 1, x z Z inverse into B 2, like that, and add it. So, this form comes very easily. Okay. X n, that is x z into B 0, x z into Z inverse, then B 1. So, there is a delay, then B 1, and this to be added because of this plus, then x z into B 2 Z inverse 2. So, Z inverse 1 into x z is already here, one more Z inverse. So, 2 delay, delayed by 2, then multiplied by B 2. Here I take B 2, and this had to be added with this result. So, that is why this summation is coming here, accumulation, with that you are adding dot dot dot. Lastly, it will be multiplied by. So, here you have got z to the power minus q into x z. Now, here B q, that will be added with whatever has been accumulated till then, is coming from this side. Okay. Sorry, it's the other way. Output. This is very simple. You can get another form by using transposition. Transposition means, actually transposition comes from graph theory. There is a transposition theorem. We will not get into that here, but that is very useful in our network analysis. But you can apply transposition here by simply following a rule that you find out the nodes. There are two kinds of nodes here. Say adder, I take adder as one node, and these are called branching points. They are adders, and then there are branching points. By transposition, what you have to do, exchange input output. Reverse direction of all arrows, and adders replaced by branching points. Adders will be replaced by branching points, and branching points will be replaced by adder. If that be the case, you apply to this, you get another structure, and this theorem says that will be equivalent to this. That is, for the same input x n, same output will be produced. So, that comes from the theorem. Since we are not giving a proof of the theorem, we will just apply these rules on this structure, derive the transpose form, and see, we will directly manually verify that they are equivalent. That is, for the same input x n, you get the same output y n. So, here the delays remain as it is, but all you see the arrows are reversed. There is a branching point. So, branching point means adder. Let me draw it in another page. There is a branching node here. So, branching node becomes adder, as I told you, and this arrows get reversed. Arrow is earlier in this direction, now it will go up. Otherwise, multiplier remains as it is, B 1. Then again the arrow gets reversed. Earlier it was in this direction, this arrow, now it will change, and this is again a branching point. So, there will be an adder. This is the output. Since we have not verified that output will be same as the previous one for the same input x n, instead of calling that y n, which is used here, let us call it y prime n. We will show that y prime n and y n are same if input is x n here also. So, these arrows are reversed. instead of going in this direction. Adders are branching, previous adders are now branching point. This arrow is reversed in this direction, earlier it was downward, now it is upward. This was this way, so this will be this way, and this is a branching point. See, adders are 2 input, 1 output device, and branching point is what? 1 input, 2 output. So, if the arrows are reversed, so there will be 2 outgoing arrow, 1 incoming arrow. So, obviously, it cannot be an adder, will be a branching point. And in the case of branching point, there was 1 incoming, 2 outgoing. So, now after reversing the direction, there will be 2 incoming, 1 outgoing. That means it cannot be a branching point, it is actually an adder. It is like that. Okay. See, the arrow reversed, there will be branching, there will be an adder. Arrow reversed, this again become branching point, because it was an adder. This arrow reversed, this arrow reversed, this arrow reversed. So, this is the input, it is going this way. Finally, again this is branching point. I give the same input now, input output exchange. This is the input now, dot 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 in this direction, right. This is a structure. These two structures are equivalent, because what is happening here is the xn is going in this path. There is adder again. Let me draw bq minus 1. Dot 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 dot. See, xn is going through this path, bq into xn, then that component gets delayed. So, bq xn, xn minus 1, that is bq xz into z inverse. There is a contribution coming from this side, they get added and move forward, but suppose I take this contribution alone separately, do not mix up with this, I will take this also separately through this path. Finally, I will add. So, this contribution goes like this, xn into bq z inverse, then again another z inverse, another z inverse, z inverse, z inverse. So, that component reaches here separately as bq into xz into z inverse q, because there are q stages. Okay, there are total q stages, b1 to bq, q stages, z inverse b1, z inverse b2, z inverse bq. So, if there are q stages, there are q z inverses. So, xz into bq into, if you take this, that signal only, do not connect these signals, okay, that consider this only separately. Then you get this part, bq into z inverse q, bq into z inverse q into xz. So, this part comes up, this into xz, and then xn goes through this again. So, xz into bq minus 1, xz into bq minus 1, this separately also goes, I am not mixing with this. Suppose this goes through it, so z inverse, z inverse, z inverse, z inverse, total q minus 1 now, 1 is gone here. So, q minus 1 times z inverse. So, bq minus 1 into z inverse q minus 1 times xz, dot 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 dot. xn goes this way, xn into b2, that contribution separately if you consider, xn into b2 into z inverse into z inverse. So, b2 xz z inverse 2 present, then xn into b1, that is xz into b1, or only one z inverse. Okay. So, b1 z inverse xz present, and lastly xz into this. So, xz into b0, this is b0, and they are all getting added. They got added here, together moved, then they got added, together moved, then they got added, moved together, moved together. So, basically all are getting added, and so you get this. If you want, you can carry out a transfer function analysis. This I leave for you as an exercise. Okay, yz by xz if you find out, y prime z by xz if you find out, you will get the same thing. That is very easy. Okay. If you apply in the case of IIR filter, this verify yourself. If you apply transposition to the direct from 1, you will get direct from 2, and if you apply transposition to direct from 2, you will get direct from 1. This you verify yourself. Now, consider a linear phase FIR filter. In the last class, I considered them. By the way, apart from this structure, FIR filter can have cascade form also. That is, if you factorize this into first order factors, and then if you have a complex root, then conjugate root also must be there. Then take those two factors, multiply, you get a second order factor, and like that. So, it will be a cascade of, it is a product of various factors, either second order or first order. Each will give rise to one sub filter, either second order or first order. You can arrange them in any order in a cascade form, and that will give you Hz. So, cascade form is available for FIR filter also. Linear phase FIR filter, as an example, suppose you have got odd length. Say H0, H1, H2, H3, H4. So, these two, this is the mirror, these two are same, and say these two are same. Okay, odd, length odd. Then what is the transfer function? Transfer function is H0 plus H1 Z inverse plus H2, this is a general form I am writing, Z inverse to H3, Z inverse 3 plus H4, Z inverse 4, right. But that is equivalent to, if you have H4 equal to H0, so you take H0 common, okay. 1 plus, then take H1 common, and then H2, Z inverse 2. So, output will be Xz into this part into H0, Xz into this into H0, plus Xz into this into H1, plus Xz into this into H2, because this transfer function Hz. So, output Yz by Xz is this. So, Xz into this whole thing, which is equivalent to Xz into the whole thing, that will be output Yz. Xz into the whole, this whole thing means Xz into this part multiplied by H0. Here Xz into this part multiplied by H1. Here Xz into this part multiplied by H2. So, this you can do like this, you see. If I proceed like this, Xn put a delay. So, this is Z inverse coming, Z inverse 2 coming, put another Z inverse. So, Z inverse 3 coming for this, and there I need another delay Z inverse 4. Now, Xz into 1 plus Z inverse 4. So, Xz and Z inverse 4 times Xz. So, you add the two first, then this addition you multiply by H0. So, this saves the multipliers. You do not have one multiplier by H0 into Xn, another H4 into Xn minus 4, and then add. Rather, you first add the two Xn and Xn minus 4, that is Xz and Z inverse 4 Xz, take H0 common. So, then you multiply by H0. So, you need H0 or H4, the multiplier only once, not twice unlike before. So, you save one multiplier. Similarly, Xz into this part. So, Xz into Z inverse 1 and Xz into Z inverse 3. So, Z inverse 1, 2, 3. So, here. So, Xz into Z inverse, Xz into Z inverse 3. So, first you add the two, then use a multiplier. Second, you are saving one multiplier. Instead of having one multiplier for this, another for this, you are using the fact that they are same. So, you are taking them common, first realizing this part Xz Z inverse, Xz Z inverse 3, and then adding them and then multiplying by H1. And then again here H2 into Z inverse 2 into Xz. So, Xz into Z inverse 2 is already available. nothing to be added. So, this I take out, multiply by H 2, and then I go on adding. I get my output. Next consider a case where the length is even. So, H 0 to H 5 will take. The mirror H 3, H 4, H 5. So, total 6. In this case, these two should be same, these two should be same, these two should be same, right. So, then you have got, that means transfer function is H 0 into 1 plus H, this H 5 is H 0. So, that will be z to the power minus 5, then H 1 and H 4 they are same. So, z inverse 1 for here and z inverse 4 for there, and H 2 and H 3 they are same. So, take H 2, z inverse 2 and z inverse 3. This is your y z by x z transfer function, which means y z will be x z into this part into H 0 plus x z into this part into H 1 plus x z into this part into H 2. So, again multiplier is saved, because you are adding this part first, then multiplying only once. Earlier you needed multiplier for H 0, multiplier for H 5 separately. So, 6 multipliers would have required, now only 3. So, what you have to do? This is your x n into 1 and z to the power minus 5. Okay. So, one delay, z inverse 1, then another delay, z inverse 2, another delay. Now, this delay, this is the interesting thing, you put a delay here. So, z inverse 2, z inverse 3, z inverse 2, z inverse 3. Then, sorry, there are 1. So, z inverse 1, z inverse 1, z inverse 1, z inverse 1. So, z inverse 4, up to that I have reached, but I need z inverse 5 also. So, one more delay. So, x z into 1 plus z inverse 5. So, 1, so x n plus x n minus 5, n minus 1, n minus 2, n minus 3, n minus 4, n minus 5. So, from here you take and multiply by H 0. Then x z into this part, x n minus 1 from here and x n minus 4 from here, z inverse 1, 2, 3, 4. This you add first and then multiply by H 1. And then add, so it is adder. And lastly, this one, x z into z inverse 2, that is here, and x z into z inverse 3, that is here. So, these two are added, and this is again multiplied by H 2. I give you an exercise, you apply transposition to these two structures for odd length and even length and get equivalent filter structures. This much I teach for filter structures. Now, we will be going for filter design, which is a very complicated, not complicated, but it requires a lot of insight, and we need analog signal processing background. So, we will take a quick review. So, we will now go for digital filter design, IIR filter design. For this, we require analog signal and systems background. Now, I am not going to give a full treatment to this, there is no time, I will quickly review. In analog systems, you have got analog functions like x a for analog t, where t is a continuous variable, say time variable. Okay. There is one important function delta function. It is Dirac delta function or impulse function. It means it is going up to infinity and 0 elsewhere. That is delta t, it is 0 as long as t is not 0. But it is not discrete, that at t equal to 0 it is something and at t not equal to 0 it is something else. Then it will be discrete, not continuous. But it is a continuous thing. So, actually it is a limiting function, that this will be 0 everywhere, and when you approach 1, it will be such area under this. I will explain, area under this will always remain 1. That is why they teach like this, that first you take a box, say maybe A minus A. So, area will be, I want to make the area 1, A minus A. So, total length is 2A. So, this is say 1 by 2A, 1 by 2A. Now, I want to make this width smaller and smaller, because this is outside this line, it is 0 everywhere. It is outside 0, for any point it is 0 everywhere. So, this has to be made thinner and thinner, but so at A decreases, 1 by 2A increases, so it will be like this. Finally, it will squeeze to 0 and this will shoot to infinity. In the limiting sense, area will be 1. Okay. This function has another property. If you take minus infinity to infinity, any function f t, say delta t minus tau d tau, what will that be? So, this is like this box here, delta t minus tau. Okay, there is a box here and this box area is 1. So, you squeeze and this will go up, finally go up and shoot up to infinity, area will remain 1, that is delta t minus tau. Around tau, this is around tau, you start with a box. Okay, so that within this box area is 1, they start squeezing. So, but keeping the area 1, so this will go up in the vertical direction, further go up as this width squeezes, finally go to, this will go to 0, this will go to infinity, but area will remain 1. That is the meaning of delta t minus tau. Delta t minus tau into f t means, first suppose I have not squeezed it fully to 0. So, f t into one of these functions, and then as you squeeze it, what happens? If you first say I have got a situation like this, this is this much and I multiply this by f t. So, it will be like this, this much will be f t into my this function I call capital delta. Okay. Capital delta. So, this capital delta into f t, this height is flat. So, f t may be time varying. So, that is why it is like this. And then as this delta, this becomes close to 0 and this shoots up. Okay. If you still consider the area under this, it will be what? It will be, this will be so narrow that it will become very narrow like this. So, but area, if this is not present, area will remain 1. Because of this, area will be multiplied by the value of f t, like it was here. So, you have to carry out the integration, but if it becomes thin enough, then integration is not required, value will be roughly f tau, and the tau center point what is the value, that will be. Okay. So, f tau into the area is 1. So, it will be f tau, that is, it will be like this, the function it will be tau, even if it is not gone fully up to infinity, but this height will no longer be modulated, it will be almost constant, because this is so narrow. So, f t into delta will amount to multiplying this very narrow delta, capital delta, with the center value of this function at tau, and area will be, so that f tau times original area, that is 1. So, f tau, and as you squeeze it, this height will go up, area will remain same, f tau into 1, this is f tau. So, finally, in the limiting case also it will be f tau. This is one property. This means any function x t can be written as x tau delta t minus tau d tau. This is like tau is varying continuously from minus infinity to infinity. So, there are impulses on this axis moving as tau changes, one impulse, another impulse, another impulse, another impulse, like that, but there is continuously moving. Each impulse is multiplied by a constant x tau and a linear combination. So, linear combination impulse functions. Okay. This is typically x t. Then if I pass it through a linear and time invariant system, linear system means any operation on this integration is summation. So, any operation on this summation will be summation of the operations. Okay. That is, if I pass it through a system T, analog system to have, sorry, it is x t, I am very sorry, to have y a t. Okay. Linear means T working on any summation, T working on a summation of signals. So, there is superposition of signals, the response will be summation of the individual responses, but summation means in this case continuous summation, that is why it will be integral. T of this will be same as integral T of whatever you have. Okay. That is, first you superimpose, then apply T, apply the system and get the response. That will be same as you apply T on the individual functions, get their overall this response and then integrate, add. So, if you do that here, if it is linear, T x a t is very much like I mean the discrete case. So, you replace x a t by this, and so T working on a summation of these functions. Here the function is delta function, delta t minus tau. Okay. Tau is variable, but function of t is delta. So, delta t minus tau, for each tau in this integral there will be a shifted delta tau multiplied by a constant x tau, amplitude factor x tau. So, x tau times one shifted delta shifted by tau, but tau is varying continuously. So, we will have shifted delta all over continuously, and this if I pass through a linear time invariant system. So, after the superimposition of the shifted deltas and then applying t on it, you will get the same thing. If you apply t on these individual deltas, this one shifted by some tau multiplied by the amplifying factor, attenuating factor, constant factor x tau, t on this, and then you vary that response over tau and get all the responses and then add, you will get the same thing because of linearity. So, that t if you bring here t on this, but this is a constant, actual function of time is this. So, capital T will work on this part. So, it will be your x tau, x a tau rather, t working on this. If t working on this one impulse, suppose I give a direct delta function the input of the system, I measure the output, I call it x h a t, impulse response. Then if it is time invariant, that is, if I give the delta after some time tau, new response will on the same time scale will be same as before, but just shifted by the same amount, delayed by the same amount tau. So, if it is time invariant, this will be h a t minus tau, which is analog convolution. Okay, and t minus tau, now I can call it, I mean you write it as x a t star h a t. Okay. Whenever you have this star is analog convolution, and then how to carry it out? First bring an integral, that is summation from minus infinity to infinity, write the first guy as the first guy, but as a function of some tau, local variable, integral variable, then bring the next guy h a, but instead of t, make it t minus tau, where tau was here. Okay. But now, in this integral t minus tau, I can call it t 1 or say t prime. Okay. Then what happens? or maybe tau prime, say t minus tau, I call it tau prime. So, tau will be t minus tau prime. This is number 1. Number 2, d tau prime is minus d tau. T, small t is fixed from outside. You want to find out output at a particular time, y a t. So, t is fixed from outside, that t is not variable. You want to find out the output at that t. Tau is variable in the integration. T minus tau I am substituting by tau prime. So, instead of tau, tau prime. So, what is tau? T minus tau prime, number 1. What is d tau prime? This same as minus d tau. T is constant in this because t is fixed from outside. And if tau goes to minus infinity, t minus infinity, so it goes to plus infinity, and vice versa, it is minus infinity. So, it will become plus infinity to minus infinity, x a, instead of tau it is t minus tau prime, instead of h a t minus tau is tau prime, and d tau is minus d tau prime. So, minus will go here, d tau prime, and this minus can be absorbed by again reversing the sign of the integral. So, in this case it is convolution between, in terms of notation it is h, because h a tau prime into x a t minus tau prime. So, h a t convolved with x a t, and take by what? This is more convenient for all analysis, okay, as we did in the discrete time case. We will continue from here in the next class, cover some more part of analog signal system before I go into the filter design issues. Thank you very much.